Welcome back to Engineering Mechanics, and today we will talk about forces in 2D spaces. So let's take a look at what our real goals are for today. So first of all, we want to reiterate our trigonometric laws so that we know how to apply them to force systems in engineering mechanics. And then we want to talk about forces and force additions. For that, we really will use vectors, so that ultimately we can compare trigonometry to 2D vector description. And then at the very end, we will hopefully be able to use vector addition and vector decomposition to describe 2D force systems, and those are planar force systems. So let's get started and recall our trigonometric laws. Of course, we remember that every time we deal with any random triangle, we really need the trigonometric laws if we want to know more about the angles or the length relationship. If it's not a right angle triangle, then we want to use the cosine law and the sine law. And this has been provided to you in previous lectures that are available for you. So let me just rewrite quickly the cosine law. Remember that c square is equal to a square plus b square minus 2ab and gamma. And that was derived in a different lecture for you. However, I want to quickly focus on these entities in the context of engineering mechanics. So first of all, how do I memorize this formula very well? It's pretty much Pythagorean theorem minus the specific angle here. And this angle is not a random angle. You really need to know how this angle is defined to use it properly in engineering mechanics. And that angle is the one between the side A and B. So for example, if I call this here side A, B, and C, then I would have a gamma angle right down there because it's enclosed between A and B. And so that is independent of how the triangle is oriented in space, because it will always relate to the angle between A and B. And it doesn't matter really if you call it A and B, as you will see later in the examples. You just have to be able to apply it properly, and that's really why we're recalling these trigonometric laws here. Similarly, for the sine law, so the sine law states nothing else than that the sine of alpha relative to side A is equal to the sine of beta relative to side B, which is equal to sine of gamma, which is relative to side C. Some people write this upside down. It really doesn't matter. However, the same thing applies here. You need to know where A is relative to B and to alpha and to gamma and so on and so forth. So if I have another random triangle here, it is just that if I have side A, B, and C, then for example here I would have my alpha. And so if I want to use this formula, I have to obviously use the proper relationship. So A would be this side, alpha would be this angle, and then B would be this side, and then beta, which would probably be an unknown, would be the angle here. And my goal next now is to explain to you where we can use these in engineering mechanics. In fact, I think we already are ready for an example, because it is just a quick review of the trigonometric laws. So let's put this to application. So here we have our very first real problem in engineering mechanics. And the first thing we always need to do when we look at problems is to really read and understand the problem statement, because we often ask you very specific techniques. And here in this case, we are asking for trigonometry. So you can, of course, use this problem or solve this problem in many other ways. For example, a lot of you probably would resort to vector decomposition, but please pay attention. This is definitely not allowed in this case, because we want to make sure that you are familiar with the technique that we need for this. So what are we supposed to do? We are supposed to determine the resultant force on the I hook and the angle that that resultant force has. So let's take a look at that problem here. we have two forces. They both pull away from the origin of the coordinate system. The first force pulls with 15 degrees, the second one with 10 degrees, and you see the amount that they are pulling here. It is always good to have a sketch first, and you may remember this from your basic physics class, that you can use your parallelogram to find the resultant in a force system. So let's do that. I first will move my F1 parallel along this line, and then I will move my F2 parallel along this line here. And now the diagonal within that trapezoid is really my resultant force. So let me put that in for you. So this would be the resultant force, or this would be the visualization of it. So F resultant is what I call that. And now we have to find that resultant force and its angle. Let me show you where the angle is. So the angle would be this distance here. And it's important that, let's call that theta, that is measured from the positive x-axis. So from the positive x-axis towards the positive y-axis, so that means counterclockwise positive. That means we're measuring in this direction. This may be very clear to you in this example, but sometimes we are in the second quadrant or the third quadrant or the fourth quadrant, but you always have to measure from the positive x to the positive y. So that would be counterclockwise positive. All right, but how do we do this now with our trigonometric laws? Remember the trigonometric laws, the cosine law, we just wrote it down. I do it once again. So c squared is equal to a squared plus b squared minus 2ab cosine gamma. So now how do I apply this here? Well, I would argue that it is easiest to apply it in the fashion that I'm looking for the f resultant. So f resultant would probably be my c, and then I have a and b. And so all that's left to do for me is to find the angle gamma, which is that angle gamma. It's the one between a and b, remember, right? So it's the angle right here. So let me maybe first transcribe the equation, and let me say that f resultant is really equal to f1 squared plus f2 squared minus 2 f1, f2, and then the cosine of an angle that I'm not aware of right now. And there lies the first challenge. So let's look at that angle first. So really I need this angle, and let me call that gamma. And gamma can be found. There are some traps here to fall into, but let's talk about them. So first of all, I know that it's a parallelogram, right? So I know that this entire figure here is a parallelogram, and therefore I know that all angles in the parallelogram, this angle plus this angle plus this angle plus this angle is 360. So I can state that 360 is equal to, and now I need to look closer again. So I have this angle, which is identical to this angle, so effectively 2 gamma, and then this angle here. Let me identify that as well. So let's say this angle here, that angle is really equal to 90 minus 10 minus 15. So I know that this angle is really equal to 65. And now, once again, I have this angle acting here and here. So all I have to do is say that 360 is equal to 2 times gamma plus 65, which is also 2 times, right? So in other words, I have 180 being equal to gamma plus 65, and therefore gamma is really equal to 180 minus 65, and that equals 115 degrees. And now I pretty much solved the problem. However, don't be fooled when you follow me on these examples. This is the starting point and the equation everybody gets right from the start. But the question is, are they able to find the angle? And now I showed you how to do that in this case. Of course, every geometric case can be different, and that's why you get the homework to practice that. So now we know 115 degrees is gamma, and now I can start solving my equation. So let's go ahead and do that. So let's say that F resultant is really equal to 100 Newton squared plus 150 Newton squared minus 2 times 150 Newton times 100 Newton times the cosine of 115 degrees. And if I solve this, by the way, this of course is F resultant squared, but if I solve this for F resultant, I will find that I now have 212.6 Newton. And so this is a result, and that result I need to double underline as always, because that is specifically what was asked of me in the problem statement. And this 212.6 Newton is effectively the length of this arrow. And so we completed the first part, which is the resultant force, but now we need to find the angle of that resultant force. So how do we do that? So the resultant force is really that purple theta there that I marked for you, this angle here. And now I will find that by using the sine law to identify this angle inside and then add the 15 to it. And there's one trap that students often fall into. Students like to believe that this angle here is equal to this angle, or if I show it down here, this angle is equal to this angle. But this is not the case. That's only true, if you think about it, for very specific types of trapezoids, and of course for a square. So don't fall into that trap. This angle is different than this one usually. And so therefore I have to calculate this angle first. So let's go ahead and do that. So my formula is, as I stated before, A to sine alpha, just as B to sine beta, for example, or C to sine gamma. Now, how do I apply this? So let me name some things here. I have my gamma here, so I have this fulfilled. And again, keep in mind that gamma is opposite to C. So opposite to C is actually my F resultant. So I already have these two fulfilled. And now if I want to find this angle here, I would have to use the opposite, which is along this line. And that is really F2, right? So now I have to use F2 here. So if this is alpha, let's pretend that's we're going to call that alpha. And let me mark that up for you. So from here to here, that's alpha. So if I want to find that angle alpha, I just have to use my F2 as A. And therefore I have F2 relative to sine alpha is equal to F resultant to sine gamma. And now all I have to do is solve this effectively for sine alpha. So I bring that to the other side, bring these over. Let's do that real quick. So that sine alpha is equal to F2 over F resultant times sine gamma. And now all I have to do is populate that with numbers. And in fact, I can immediately state that alpha is equal to sine inverse of my F2 was 150 Newton. And my F resultant was 212.6 Newton. And then I multiply that by sine gamma, which was sine 115 degrees. And that gives me my alpha angle. And that alpha angle happens to be 39.8 degrees. However, be careful, because that's not the true answer here. We're not looking for that angle. We're actually looking for the angle theta, right? We're looking for this angle from here to here. So I now have to add 15 degrees to it. So let's do that in our last step. So my theta is really equal to 39.8 degrees plus 15 degrees, and that is equal to 54.8 degrees. And that, once again, is an answer to what was really asked of us. I only have to find and double underline the answer to what's really asked. And of course, I always add my answer arrow. And I have to do that for my first answer as well. Of course, here in the lecture, that's different than on engineering paper. But that concludes this problem. And so therefore, I have my answers provided. Let me reiterate real quick that the downfall of this problem is not actual solving the solution, as many things in mechanics. It's not solving the numerical part. It's usually setting up the equation and finding the starting point. So when students in the exam usually get this wrong, they usually mess this one up. And that is something which, you know, I can show you in this case, but again, you need to practice that for different geometric features or different geometric arrangements. So please try to study up on that and get ready for that, because this is effectively a good problem number one on an exam. But this concludes the trigonometry part, and now we can move on to vector analysis. So of course, if you made it to engineering mechanics, you already passed your physics classes and you have an understanding of vectors, and you've seen it in mathematics classes as well. Let me reiterate it anyways, just so that we're all on the same page. So first of all, vectors have a direction and a magnitude, right? Direction plus magnitude. And that is important because some physical concepts cannot be explained by just a number. In fact, let me make a side note here. If you have just a single number like a scalar, then you can describe things like temperature. You can describe things like mass, and so on and so forth. However, if you talk about forces, they have not just a magnitude, like the mass does, for example. It has also a direction. And therefore, you need to use at minimum vectors. Therefore, it's important to really identify them properly. So here in the lecture, you always have to identify them with an arrowhead, or some people also put a single line underneath it. In a book, you would probably find a very bold-faced letter, right, like this. But here in the lecture, I will use something like A to describe a vector. Or if I would be really neat, I probably should do this. And that is important to differentiate from something like this, because that would be just a scalar, and that is physically very different than a vector, and so you are encouraged to always properly identify that. So do not use this for vectors. Always show that there is actually an arrowhead above it. So the direction is usually given by a plus or minus sign. And the magnitude is usually the length, and it's also positive because the length is always positive, right? So magnitude always positive, which is the length. And then let us real quick remember that when we draw them, what is what entity? So for example, if I have a coordinate system here, I have a vector in that coordinate system, and pretty much this is the length, and the direction is given here. So that I can describe it by the angle alpha that it has relative to the horizontal most often. And keep in mind that this part here we call the tail, and this here we call the head. All right, so now we obviously recall what vectors are, and we probably also recall the basic mathematical rules. So if you multiply it with a scalar, for example, then let's say you have something like the scalar a times vector a would be nothing else than a times ax, a times ay. And today is the last time we write vectors like this. Some of you do that. I will come back to that. I'm just going to use this right now, this notation, because that's what most of you are used to. However, this is no different than ax and ay. And that means that we can, of course, multiply the individual components by the scalar. And if you know how to multiply, then you can also do division, because if you, let's say, you have a divided by b, then that's just the same as 1 over b times a. And so therefore it's the same rule, which is 1 over b times ax and 1 over b times ay. And so on and so forth. But of course, we do remember this. In engineering mechanics, of course, we usually deal with forces. So let's say you have, for example, 5 times 7, 8 newtons. And so that would equate to 35 and 40 newtons. Let's talk about vector addition, which is a little bit more fun, and that is because we have a visualization problem here. So let's say I have a tabletop, and on that tabletop I will place myself at point 0. So this is point 0. And now I'm going to walk on that tabletop. And I'm going to walk along this line. So this is where I walk. I call that vector Raphael. But now there's a student who may not like me or something like that and wants to try to pull the table in this direction. And so every point of the table really moves along that direction, so that the table ultimately ends up somewhere like here. Including the starting point. Right? So that the table at the end is in a different location. So I can actually use the arrow and move it parallel so that now it's here. And if both happens at the same time and you stand here and you watch at the system or you look at the system, then what you would see would be pretty much vector addition, which would be this arrow here. So if I call this here student, then the red vector here would be r plus s. And of course they are vectors, so I should follow my own rules here. And so vector addition is really nothing else than combining the two vectors to form the third one, pretty much as it was visualized here. However, it's an important aspect that we will use in engineering mechanics, so therefore let's talk a little bit more about it. So you probably have done the vector addition before, and you may have used one of two methods. And one method is called the head to tail technique. So head to tail method or technique. And the way that one works is if you have two vectors that are somewhere random in space and relative to each other, and keep in mind that you can always move vectors parallel along their own line, right? So let's say I have vector A here and vector B here, and now I can move them parallel. I'm going to use a different color for one of them so that you can better follow that. So I'm going to move the first one parallel, and I'm going to move it head to tail. And of course, this has to have the same length. So this here is vector A. And now my resultant vector, similar to what we actually seen before, in fact, we kind of used this in our first example, is shown here now. So this is what we called F resultant before. Here, let's call it vector C. So that's the head to tail technique, and that always works. In fact, you may want to also know that you can do it the other way around. So for example, you could have the blue vector somewhere down here, which was called vector A. And then you can actually attach vector B to it. So let me get that parallel. And let me move that so that it will fit. So this now would be vector B. And of course, they have to be identical to each other. So A plus B is equal to B plus C. That's really the story that I'm trying to send here. So let's write that down. So A vector plus B vector is equal to B plus C. And that is an important rule that applies to vector addition. There is another technique called the Parallelogram Technique. And that is very similar to also what we've seen before. So let's have our two vectors again. I have vector A and let's say a vector B. So this is B, this is A. And now I use my parallelogram technique where I just move each of these parallel to each other. So I would have this B parallel, and then I'm going to move A parallel. And where those meet, or the diagonal along the parallelogram, is really my resultant force. So I have a resultant force here, or any resultant really. I'm going to call that C. A vector and B vector. And once again, this rule up here applies, because it doesn't matter in which direction you do that. So please keep that in mind. A plus B is equal to B plus C. Now, of course, you can do that multiple times or consecutively. And my favorite examples for this is when I take my animals for a walk. So let's go on a walk with my animals. Let's say I'm standing right here. This is my starting point, Raphael. And I'm bringing my dog. And my dog is very strong and it pulls me in this direction. So let's call that a dog. But I also have two cats, so I'll bring these two. So here's my cat 1. And let's say the other cat is a little bit more afraid. So let's say that she wants to move in this direction. And maybe I'll even bring my hamster. I guess my hamster should be a little bit weaker than the rest of the bunch. And so now the question is, where will I go if all these animals pull on me in that direction as shown here? And the answer is you can use the head to tail technique or the parallelogram technique multiple times. I'm just gonna show you how that applies. I'm gonna start with my dog, and then just to be random, I follow by cat 1, by cat 2 I should say. So that would mean that I move in this direction. And then the hamster was going in this direction. And the cat moves in this direction. And ultimately, I, Raphael, would be pulled in the direction from my starting point to the end point of that head to tail method. So this is the direction I would be pulled. Of course, if this is called the action force, right? So that's the action that the animals apply to me. However, if I want to somehow resist that, and I want to stand still, I have to apply Newton's third law and actually pull in the opposite direction. So this would be reaction Raphael. And so therefore you now understand how to add multiple times the vectors. Of course, numerically, there might be smarter ways to do that, but this method always works, and that goes hand in hand with vector addition. And with that, I believe we're now ready to talk about vector subtraction. So let's move on. So vector subtraction is actually no different from vector addition. In fact, let's ask ourselves, what is a negative vector? So a negative vector is a vector that is parallel but opposite in direction. So let's say I have vector A here, and I want to know what the negative A is, then it would just be minus A. And so now, if you know that, you can actually use the same technique, right? Because you have, let's say, A minus B vector would be nothing else than A plus minus B. And so let's have a sketch for that as well. Let's say I have a vector A, and I have a vector B, and let's say that is here. And now I want to know what is A minus B. So I take my B and turn it into minus first. So that would pretty much look like this. So this would be minus B. And now I have to use the head to tail technique. I guess I'm going to do that a little bit on the side so that I do not end up in my own drawing here. So let me move this. And now I can add my negative vector via the head to tail technique in this direction. So this is minus B. And so my ultimate C vector now has to go from the starting point to the end point of this. So this would be C. And so C is equal to A minus B. But also notice that C plus B is equal to A. Of course, this is just rearranging the formula. But it can also be seen here that if you have C plus B, you end up with A, right? B would be in the opposite direction of negative B, and so therefore C plus B would be A. And that concludes vector subtraction. We should now have a good understanding conceptually of that. So let's move on to vector decomposition. And why is that important? Because often you actually have to do the reverse. Instead of adding two vectors, you have to break them down into their individual components. I'm pretty sure you have seen this before, but let's talk about it anyways. So we have an x-axis and a y-axis, and within that y-axis and x-axis we have a vector, and that vector could be randomly arranged. So let's call this here f1. And of course, we know from high school that we have these components here. This here would be usually what we called f1x. And then we also have the value from here to here, which we will call f1y. And many of you are probably used to writing that f1 is equal to f1x, f1y, and then using curly brackets. But that is something that from now on we will never use ever again. We also won't use something like f1x, f1y. Also a very common method to write this down for students who came just out of high school or who came from other fields. But this is not what we use in engineering. This is from now on point deduction. And why is that? Because of something you have seen before, and that is called the base vectors. And the base vectors are mutually perpendicular to each other, and they have a length of 1. We will write this down in just a second. So this is different from a unit vector. It is a unit vector too, but we have a base vector called I hat, and j hat, and I hat clearly goes along the x-axis, whereas j hat goes along the y-axis, and those define the vector space. And let's write that down, that I hat and j hat are the base vectors in 2D. And those define our vector space. And therefore, from now on, we will always write our vectors, f1 for example, as f1x multiplied by I hat plus f1y multiplied by j hat. And we put that in parentheses, and then we usually put a unit behind it. Let's say this is a force, so that you always represent these vectors this way. And let me explain that. So this here would be a scalar, right? This is a scalar quantity, whereas this is a vector. And same is true here, scalar and vector. And the reasons engineers prefer this is because they can avoid dealing with vectors whenever possible, or they can do scalar operations on the components. So let's memorize that from now on we will always write our results in this format, or all our vectors in that format, so that we can deal really with only those quantities, vector quantities, when we really have to. You of course know already that f1 is really the magnitude f1x squared plus f1y squared. This is Pythagorean, and this works in 2D and in 3D, and so that is something you need to always have under your belt. And here I forgot my vector sign, but now it is complete. So let's look at that. And last but not least, for vectors, you always will need a direction, right? So you will always have to define the angle alpha here, let's call it. So let me include that. Let's say the angle alpha here, alpha. And of course, in this particular case, because we're in the first quadrant and we're measuring from the horizontal axis, alpha is really equal to the tangent of, or the inverse tangent of f1y over f1x. So that's rise over run. However, sometimes that leads to incorrect results. So be careful when you use this formula. And I encourage you to think about what happens if you use this formula in the second quadrant, what happens if you use it in the third quadrant, what happens if you use it in the fourth quadrant. These angle alpha will come out differently. And memorize that we always measure from the positive x to the positive y-axis. So let me give you one example, although I want to encourage you to think about this yourself, but because this goes wrong so many times on exams, let me just show you what happens if you have a force in the second quadrant. So let's say we have an x-y coordinate system here, and your force is really acting in this direction. If you now use the tangent function, you will not find the angle that's relevant. You will actually find this angle here. You would find this alpha, because rise over run will give you that enclosed angle. But what's really asked of you at all times is this angle theta. So that is something you need to keep in mind. And again, please be aware that depending on which quadrant you find your resultant in, this will be different and you have to interact differently with that. But that completes the vector decomposition, and please understand that from now on you will always write vectors like this. You will also include the magnitude and you will include the direction. In fact, let me underline that as well, because you need to memorize that every result that you present for vectors will always contain three pieces of information. So results for vectors always include three sub-answers. So it's not really complete if you forget either one of them. Don't get me wrong, you can also use unit vector instead of the angle, for example, but you always have to have three entities. You have the components, you have the magnitude, and you have the angle. And that is always the minimum you have to report. But I believe that concludes our vector decomposition, how we will act with that here in engineering mechanics from now on. And so now we are ready for our examples. So here you see our next engineering mechanics problem, force vectors acting on a hook. And as always, let's read the problem statement first. So here we have to use vector decomposition method to calculate the resultant force on the I hook. And then you also need to find the angle relative to the positive x-axis. And I want to point one important thing out here. This is actually mentioned in one of the previous lectures that hopefully you read up on, because it's a very basic concept that we use all the time in engineering mechanics. And it's something you should be familiar with before you come to the class. But it's written out for you in detail. And I will explain it now here, just so that we're all on the same page. So this is called the 3, 4, 5 triangle. And what students tend to do when they see this problem first is they try to convert this into an angle. They try to calculate the angle here and then figure out the components for this force. But I will avoid this now, and you will see that A is much faster and it saves a lot of time on my exam. And B, it's much more precise because I'm dealing with fractions. So let's go through the problem in total and let's see what we have. So maybe it's best for me to write down all my forces first. So for example, F1 is equal to 300 I hat plus 0 j hat. And that is in Newton. My F2 is really equal to 400, and I'm going to use a different way to write this now, 400 cosine 30 I hat plus sine 30 j hat. So for those of you who are puzzled by this, right, so the x component actually is always the x value is always defined by the cosine function, and the sine function always defines the y value if you always measure from the positive x to the positive y. That is also explained in the written lecture where I explained the 3, 4, 5 triangle. So please read up on this if this is confusing you. However, I need to include my unit here. So these are newtons. And now I have my last force, F3. And now this might go fast for you, but again, you can read up on this. This is available in the lecture script in the very beginning in one of the 0 lectures. So 250 Newton has to be really divided by 5 and multiplied by 4 to be the I component. And that is positive. Now I need to be careful because the j component is negative, and that is divided by 5 and multiplied by 3 j hat. And now I have all my components of all my forces written down here. So the last thing I need to do now is vector addition, and I just need to combine all these numbers. So let's write that down. So my F resultant is really equal to 300 plus 400 cosine 30 plus 254 over 5, and all of this is I hat. And then I need the j components, which are 0 plus 400 times sine 30. And be careful now, minus 250 times 3 over 5. And that is all multiplied by j hat. And I cannot forget that this has a unit. Otherwise I lose valuable points. And in this case, we're dealing with newtons. So now my F resultant can be calculated. And that turns out to be 446.4 I hat plus 350 J hat. And again, don't forget the newtons, and this is one part of my answer, so I better double underline it. So there we go. And now I need to find the magnitude of that F resultant. So F resultant magnitude is equal to 446.4 squared plus 350 squared, and the whole thing square rooted. And that turns out to be 567.3 Newton. Of course, if you punch that into a calculator, you will actually end up with like more digits, but keep in mind our 4 significant figures rule. That's also listed in one of the previous lectures. So do not list more than 4 significant figures. You would lose points. So that's what I'm doing here. And last but not least, I now need to find out if my resultant force has an angle to the x-axis. And to do that, it's always good to look at your sketch, because again, you need to know if it's in the first or second quadrant. And in this case, you see that all the numbers are positive. So that means that you are in this quadrant, so your tangent function works. So I can do that. But before I do that, let me just draw that resultant force so that you clearly know what's going on here and what numbers have we calculated. So this was equal to 567.3, and then we had a x component which is given here and a y component which is given here. And so x would be equal to, what did we calculate, 446.4, whereas the y component would be equal to 350. And so just to be clear, what I'm trying to calculate now is this angle, let's call it theta. So theta then can be calculated by rise over run in this case. So theta is equal to tangent inverse of 350 divided by 446.4, and that turns out to be 38.1 degrees. And last but not least, double underline it. And here we go. And this completes this particular problem. And I believe everyone should be able to solve problems like this now. Of course, to emphasize this and to practice this, you have homework assignments that deal exactly with these concepts. But this now finishes this problem. And we, of course, gave our 3 standard answers for vector problems. And therefore, we're done. Let's move on. So here we have our last problem in the lecture, and this one states that we are supposed to find the resultant vector, specifically its x and y components, but notice that no specific method is required here. Of course, in this case, I would argue that if it asks you for x and y components, that the vector decomposition is simpler. However, you could use any method you really wanted to. And this problem is very similar to the previous one, except that you're now dealing with angles outside of the 90-degree turn here. So I'm not going to solve this problem actually for you. I'm only going to give you some hints and the final results so that you can solve this and check your work at home. The first hint I want to give you is here the 5, 12, 13 triangle. This is similar to the 4, 5 triangle in the fact that here you will definitely end up with a 90-degree angle if you have a side length that is 5, a side length that is 12, and a side length that is 13. So you can relate these to each other. And just because that is often new, I can tell you that F2x, for example, would be equal to 260 Newton divided by 13 multiplied by 12. right? So that is because the 260 is parallel to 13, so I put that here, and the 12 is what I'm trying to find, so I put that here. And the same would be true for y. However, be careful that you understand that we're moving in a negative direction here. In fact, that gives me a chance to talk about something else that sometimes I see go wrong for students, and that is the direction of the components. So the way I like to look at this is, if I want to go in this direction from the top to the bottom, I can either walk along the diagonal or I can walk down first and then to the right. But what sometimes happens, and I will erase this in a second, is that students actually show me a triangle like this. And that, of course, does not work. So please do not do that. Please be careful. Let me erase that. So yeah, stay away from that, please. That is something that can go wrong. Then another thing that I need to point out here that is very important as you move on through the lecture is that this 30 degrees is often used for students to find the y component. So the way they calculate this is by saying that f1x is actually equal to 200 times sine 30, which is absolutely correct, but it's a bad habit to form, right? So this is correct, but I would still stay away from it. In fact, I would say that f1x is equal to 200 times cosine 90 plus 30, which of course numerically in this case is the same value. However, this method is much more foolproof and bulletproof when you deal with like more complex systems later on. So what I'm trying to really tell you here, and what I want you to form as a habit, is to always move an angle from the positive x to the positive y, and so therefore it's counterclockwise, right? So always measure your angles counterclockwise from the positive x to the positive y. That is very important. When you solve problems like this, you might get away with what's given here on the top, but so this will work, of course, and if you do it rigorously and always correct, it's fine. But I see this leading to problems when the problems become more complex. So if you form a habit and use the unit circle, in which it's always measured from the positive x to the positive y, you are much better off memorizing that cosine is always x, the x component, and sine always leads to the y component. And when you do that, by the way, you never have to worry about positives or negatives. In fact, if you type this into your calculator, you will find that you will find the negative component here. So it will automatically be a negative value. Whereas this one, you have to do that yourself. And again, if that's a complex problem, that can become tricky. So I, in my life, decided that I always use the angle measured from the positive x-axis. And of course, then the same is true for the y direction, right? So I would say that f1y is really equal to 200 times sine of 90 plus 30. And that will help you. And then again, I say it one last time, whatever you do down here, it is worth it to really internalize this here for the rest of your career as an engineer, because this will make your life much easier than using angles and try to use strange numbers here. You just make your life more difficult. That doesn't need to be the case. So please stay away from that. And with that said, I think you have all the tools you need now. So let me give you the final results so that you can actually check your answer. So I can tell you that F resultant here in this case has components of 140 I hat and 73.2 J hat. And F resultant magnitude is really equal then to, I mean, that everybody can calculate easily, I guess, from the number that I've provided, 158 Newton. And then we have theta, which is equal to 27.6 degrees. And of course, all of these are results. So I double underline them for you. I don't want to lose points. I hear the teacher is very strict about that in this class, so I better double underline this. And of course, I'm going to give my answer arrow here. All right, and I believe this gives you all the information you need to solve this problem, and also all the information you need to really complete any assignment in this lecture and with the concept of vector decomposition or using trigonometric laws. So let's take a look at our boxes here at the end. I highly recommend that you take these very seriously. So ask yourself what you take away from this lecture and just summarize 2-3 points, what you have personally learned, and then make sure that you understand what you don't know yet. This will help you a lot when you study, and it will help you a lot to clarify your questions. In fact, you probably should also think about what you want to do to get more clarification. Because ultimately, our ultimate goal here was to use and understand a few concepts. And let's go through them and check them off if we can. So do I master my geometry and sine and cosine? I believe we do. I definitely know how to use the trigonometric laws properly now. That is what we covered in the first part of the lecture. And I know how they apply to physical systems now, right? So this is something where you don't just do A, B, C or alpha, beta, gamma. You now have to actually arrange them according to a physical system that's given to you. But I believe that was shown properly, so we can check that off as well. Now, the basic 2D vector operations have been explained to me, so I think I can check that off as well. And then I want to, of course, be able to differentiate which technique is better for which problem. And this comes really a little bit more through different homework assignments and so on, and you have a chance to practice that, but I think I can check that off too, because we talked about in which case one is easier or better suited than the other. The similar triangle method is very important for me here, so that is something that engineers need to master. Again, you have that in lecture 0 already listed if you need to read up more on that. But that is something I definitely master at this point. And of course, I know now how to physically implement all these concepts. So that means we are now ready to take a look at the homework. So let's take a look at the homework problems, and let me give you some clarification here, because often some of these can be tricky depending on the variables that you use. So let's go through them one by one. So here you see the trigonometric laws, right? That is what you have to use here. Yes, you can solve this with vector decomposition, but you would get 0 points if you do that. So please use the trigonometric laws. Now, what I want to alert you to is the fact that F2 and beta are connected to each other, and that F1 and alpha are connected to each other. So often students come to me and they tell me, hey, my beta is actually larger than my alpha. What should I do now? This sketch doesn't make sense. And that's not true. The sketch still makes sense. You just have to redraw it. So in that case, if your beta is larger than your alpha, then your F2 moves up and your F1 moves down, and you can still solve it. Of course, you have to use a little bit different algorithm than some of your colleagues or classmates who have different variables. However, you can still solve it. The best thing to do for all of these problems is anyways to draw a sketch that is true to your variables. And I'll be very honest with you, with so many students in this class, sometimes it's not possible to have all variables match to each problem. So that means that sometimes there's a problem that you may not be able to solve. That is not the case for this problem. Everybody, no matter what the variables are, will be able to solve this. But I will show you later that this can be the case, and I will tell you what to do then. However, for now, please understand that you have a relationship between F1 and alpha, F2 and beta. Let's take a look at the next problem. So here I think it's very clear that you have a force along the x-axis and a force that is in the second quadrant, and all you have to do now is find the resultant, and look that here you are not required to use any specific method. Use whichever method works best for you. I recommend that you use the one that is more difficult to you, right? So often students tend to do the one that is like faster, or the one that they are familiar with, but that is not the way you should study. You should study such that you use the method that is difficult, because you don't want to be faced with a difficult problem or a concept that is difficult to you when you're in an exam. And that's when you have to do it. You have to use a specific method. So when you have the choice, I recommend you always choose the harder one. All right, let's take a look at this one. So here is a trigonometry problem. You are required to use trigonometry and then use vector decomposition to verify these results. And many times students come to me and say they don't match. What should I do? It's really not correct. And you have to be careful here, because first of all, if your alpha plus your gamma is larger than 90 degrees, the sketch is not true anymore. So if alpha plus gamma larger than 90, then you need to redraw. I mean, you should always redraw, but in this case you definitely need to, because otherwise you will get super confused. Because if this is the case, that means that effectively your vectors are looking like this, let's say, and so your resultant force would go into the third or fourth quadrant. And so that is when it becomes really difficult to use the sketch that you currently see there. So please keep that in mind. And then also, sometimes there's something called the ambiguous case when you use the trigonometric laws. When you use like a triangle, there's when you use the cosine law, I should say. So there's the ambiguous case, which can give you very difficult time. That really depends on your variables, what your f2 and your alpha is, and so on and so forth. But you will have to write that in this case you cannot solve it because of that and that. So you have to provide an explanation, and you have to then explain which method you trust, the vector decomposition or the trigonometric law version. So that was that problem. Then here we have a vector problem where you need to determine the angle such that the resultant force is directed along the positive x-axis. So that is something that prepares you for the future. We have not talked about this specifically in this class, but we want you to think ahead, and we purposely don't give you all the information, but what we want you to do is find this angle that makes sure that the resultant force of these two is acted directly along the x-axis. Once again, depending on your variables, there are cases where it's not possible to solve this. And you have to explain that in words why it's not possible to solve this if this applies to you. The majority of you will, however, be able to solve this properly based on their variables. All right, last but not least, we have these problems here waiting for you. And I think the only two I need to talk about is probably this one up here. So notice that we have a force that is pulling up, and that force is F1 plus F3. And you need to define FB and FA so that equilibrium is really created at that point. So we want to balance FA and FB by that force. And I believe that should be manageable with what we talked about in this class. And here, don't be fooled. I mean, the idea is, of course, to put you into like a little thinking pattern, but the only thing you have to do probably is turn your page here and look at it in a different way if you want to solve this problem. Other than that, I believe we're now well prepared and we are ready to tackle our first real engineering mechanics homework problems and enjoy the vector application and the trigonometric law. I wish you good luck with that, and I'll see you in the next lecture.